Hello, hope everybody's doing well out there. So, just a quick recap. Hopefully, you made it through designing an experiment, how you're going to take data, what inputs you're going to measure, what outputs you're interested in, revisit the goals and working criteria of your project, and think through what pieces of that are you meeting. And then once you have that experiment planned out, the next step is to actually take data, measure something, whether it's strength or energy efficiency, ease of use. You could, talk to the neighbors or friends, ask them to try it out and give you suggestions. And then after you test it and get that data, the final step is to redesign. So take into consideration tests and that data that you did and make what you built just a little bit better. Nothing out there is perfect. There is no perfect car, no perfect house. Everything can always be redesigned to be just a little bit better. And that is the point of testing. And that's how progress is made, is just fixing things and updating things every single year just to make it a little bit better. As part of this, I wanted to introduce everybody to some simple machine concepts which are used throughout mechanics classes and mechanical engineering. And there are different ways of taking large forces and turning them into small, manageable forces. So these are things like levers and pulleys and wedges, screw, wheel and axle, and inclined plane. So what was very difficult to lift and move around becomes very easy to move around by using some of these little tools that we have here. There is a quiz that goes through some of these concepts. I went ahead and made this quiz bonus because I want everybody to really concentrate on modifying their project this week. So your number one priority, work with your team, update, modify your project, do some research, see how you can make what you built just a little bit better, document that, take a picture of the original build, and then take a new picture of what you updated based on it. And then this quiz, it goes through principles of how to use gears and pulleys and levers and just take large forces and turn them into small forces. So I'm going to go through a few notes, and there's some PowerPoints that are attached in the content for this, but it is bonus. And so some of these concepts, if you have not made it through Physics 1 yet, if you have not seen any mechanics classes yet, and this is just really frustrating to get through, you do not have to get through it. It's just a bonus, but hopefully it will introduce ideas on some of the magic of mechanical engineering, of being able to move mountains very easily. And it's these games you play with forces and force ratios that allows us to do that. So I'd like to just start the discussion of simple machines with a lever arm. This is a PhET simulation from Colorado University, Boulder, back from where I'm at. So let's say you have this huge weight, and maybe you just are not strong enough to lift this thing on your own. Maybe this is the maximum of what you can move around. So you want to be able to move this huge weight with a teeny tiny little force. So that's where lever arms come into play, and there's a couple of different ways you can set this up. The idea is to twist something, to turn something, it takes two things. It takes a distance as well as a force. So for rotational motion, it's not just a force. You have to have a lever arm, and that force needs to be 90 degrees perpendicular to the lever arm. So if you consider like a wrench, if I'm just pushing in the same direction, Fx here is not rotating it. Fy is the piece that's rotating it. And you can move quite a lot around using lever arms. There's a couple different ways to set these up. Class 1 is what I just showed you in the PhET simulation. So you have the effort, that's what you put into it, versus the load, that's the big rock or whatever that you're trying to move. So you can put that rotation axis in the middle of this thing and play around with those distances. The other way to do this is to actually have the rotation at the corner and put the effort on. So this would be like a wheelbarrow. If this was the wheel on your wheelbarrow and the handles and you're pushing it up and then you have a big pile of rocks in the middle of your wheelbarrow, that's what a class 2 lever would look like. Class 3, this is actually like your arm. So this could be your shoulder. The effort is your muscle, and the load, that could be a bowling ball or some textbook in your hand that your muscles are then moving around and it's pivoting around your shoulder. So these are the class 1, 2, 3 levers, and this is in the quiz to kind of identify some examples of these different levers. Okay, back to our example. So amazing thing that you can move these great big forces around with just a small force, but it comes with a caveat, and that is the amount of displacement. So how far you move something is going to be a function of how far away from that axis of rotation that you are. So if you consider a circle, one that is centered with its edge on the very large load, and one that is centered with its edge on the very small load, and consider the arc length that each of these moves. So if I move the large load, maybe, I don't know, 30 degrees or something, how much distance has it gone up and down versus how much distance has the little 5 kilograms gone up and down? So the trade-off here is that this end of the lever arm is going to have to move quite a lot. So you have a very large movement with a small force to get a very small movement out of the large force. But you can still move that large force around. So that's pretty cool. Okay, some other ways to see this. Let's say I have not a lever arm, but a gear, and a small gear that is hooked next to a large gear. So if I have a large lever arm and a small force, that will give me the same torque as a small lever arm and a large force. So this is a transmission in your car, gearboxes in toys. If you have any kind of a motor in your project, and you want to look between RPMs, or you're having a hard time with forces and you want some kind of a large force out of a small force, you can do the same thing with a gear, and it's exactly the same as that simulation. So you have a small radius to a large force will balance a large radius to a small force. And there is also a similar relationship between how those two sides are moving around. So the side with a small force and large radius, let me just pull this up again and maybe think through the number of teeth. Let's say this little gear only has 10 teeth and this one has 20. So if this one turns a full revolution, so 10 teeth, click, 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 it's gotten 10 teeth, how far is a 20 tooth turned? So 10 teeth would be half of the circumference, and as this little gear has rotated around an entire revolution, the large gear has only gone around half of that. So the same kind of deal. So to match those forces versus to match the RPMs, the small gear will be rotating quite a bit faster than the larger gear. A good example for gears is to think about how your bike works. So you have bike pedals, how fast your feet are going, and the force from your feet. And you also have gears in the back that are connected to your back tire that control how fast your tire is rotating. So let's think through a couple of gear ratios. Let's say your foot is out here at a large radius and the chain is on a sprocket on a small radius. What does that mean about the force from your foot and the force in the gear? So your foot force with a large radius is going to translate to an even larger force for this small. So large radius. Let's pull up that simulation again. So let's say your foot is out here at a long radius, only 5 kilograms, and then you're going to have a small radius on that sprocket that now has a really big force. So that's pretty cool. Like your little foot on the pedal is going to move quite a larger amount of force going on here. But you have to think through how that is going to translate to how fast your back tire is rotating. Remember, the small gear is going to rotate faster than the big gear. So if the small gear had 10 teeth and the big gear had 20, the small gear going around once means the back gear has only gone around half a turn. So that's why when you gear down on your bike, yeah, it's a smaller force, it's easier to pedal, but you're going to have to pedal faster to go the same distance. If you switch this around, maybe you're going downhill instead of uphill, you can then put your chain on a larger sprocket where your pedals are and connect it to a smaller sprocket where your back tire. In this scenario, you'd have to push down with a much larger force on your bike pedal, but remember the small gear, it's going to be rotating at a much faster RPM, and it all depends on that gear ratio. So how many times is a small gear, which is connected to your entire back tire? So how much is this guy rotating? What's that RPM with relation to your pedal RPM, which is connected to these gears here? So next time, and I'll give you maybe some bonus points if you go on a bike ride, and then just really think through those gear ratios and how those gears are working, because that's a great application. And that is one of the simple machines, is gears. And it goes through transmissions and gearboxes and motors. It's hard to find a mechanical tool that doesn't have a gear in there somewhere. Okay, so there is levers, and that actually kind of gets into a bit of wheel and axle. There is also a screw. That is one of the simple machines. And let me scroll down here. A good application for a screw would be a vice grip. Okay, so here's your screw. And you can imagine, putting a piece of wood in here. It's a very large gripping force for a very small force to turn this screw. So this is a ramp. You can think of those threads wrapped around there like a ramp, which is another simple machine. And it's the difference between like driving your car straight up the side of a building versus using the ramp in the parking garage at the airport. This is a fun thing to go around if you've been to the airport downtown. Okay, so that little ramp is wrapped around. As you rotate this 360, usually for a single threaded screw, you travel the distance of the pitch between those threads. So once around, you've moved this only a millimeter. So a large distance to a small distance, but it goes from a small force to a large force, a very large force. So screw is another one of those simple machines, and you can see some example calculations here. This is from a statics class. And you can model that ramp that twists up the side of the screw with a block and a wedge, drawing free body diagrams. So for all of these mechanical systems and most engineering applications, it all comes down to understanding forces. And if you take physics or mechanics classes, you will analyze systems by drawing a piece of it, drawing arrows that represent maybe the weight of the object or the ground pushing up on the object. You can think about the friction acting on that. And then you add these arrows together, which are called vectors. They have a length and also a direction. And that is how you walk around these things. So for statics, all of those vectors will form a closed loop. Everything in the vertical direction cancels out. Everything in the horizontal direction cancels out. And you can see what forces would just barely balance one another. For dynamic systems that are moving, the vectors are not equal and opposite. They don't cancel out. And whatever is lopsided and doesn't cancel out, F equals ma. That's which way the thing is accelerating. And that can be angular acceleration or linear acceleration. So I've copied in the PowerPoint here a couple of example mechanics problems that you can study and try them out in that Simple Machines quiz. If you're around on the campus, I can go through some of these, or I can talk with you through WebEx if you're interested more in thinking through things. So it has a wheel and axle and really thinking through how those guys are interacting and what force. So here's the weight being held up, and that is held up in part by friction and in part by a normal force. That one's kind of a tricky one to analyze. There are pulleys. Let me scroll down here to the pulley problems. Those are another really fun thing. Maybe you have one set up in your garage. So for these, you count the strings. Let me just grab an example. The effort is going to be how much you have to pull on one side of it, and the weight that you lift. So the mechanical advantage is a ratio of how much you have to tug on it versus how much you're lifting up. So for this case, I'm going to carve out just this piece of it. So when you make free body diagrams, and this is for any complicated system, you take that complicated system and you just carve it up. So you look at one small piece at a time and start with what you know the most about, and then work your way over to what you know the least about. So here's an example pulley. Let's say I've got 100 newtons. So newtons is force. It's a kilogram times 9.81 meters per second squared on Earth. So it's mass times gravity. And you can see if I carve this section out of it, that this 100 Newton force is held up by 3 different cables. So if I look at the forces in the y direction for this system, what I will have is 3 tensions that are holding up the weight, 100 newtons. And if it's static, if this is not moving, so no acceleration going on, then that would add to 0. And what we can have then is that tension is equal to 100 divided by 3, or 33.33333. So if you take this tension and you can kind of trace it getting wrapped around and wrapped around again and wrapped around again, and then over here, this is the side that somebody is over here pulling this weight, right? Grr. That, how much they're pulling, that's going to be only 33. That's your 100 divided by 3. So there's your mechanical advantage. So I can lift 100 pounds. This is a huge weight with only 33 pounds. And so you would say your mechanical advantage is 100 divided by 3 equals, you're getting an advantage of 3 here. And depending on how many times you wrap that cable around, you get larger and larger mechanical advantages, with the caveat that the effort side is going to have a very large displacement compared to the load side will have teeny tiny little displacements. So you can move it with a small force, but you're going to have to really pull in that rope, and it's like a bike tire. So you pedal your feet fast and you don't go very far, but at least it's a small force. So whatever you gain for mechanical advantage, you usually lose with displacement, and that's like a ramp. So if you have a smaller angle for your ramp, yeah, it's easier to lift, but it's going to be a much longer ramp to get you to where you're going. And that's That's the trade-off for mechanical engineering. Okay, so chat with me if you would like another WebEx to go through some of the stuff in the quiz. And it is kind of fun that you can take very large forces and move them with very small forces and play these games with vectors to create systems that have large mechanical advantages. And this is kind of the point of mechanical engineering, is to make life easy on yourself, to be able to move large objects around very easily. And you can do that a number of different ways. So there are lever arms, pulleys. A wedge is very similar to inclined plane and screw. Those are kind of all related to one another. Wheel and axle, there's an example in here of like moving a dishwasher around, right? So if you're going to scoot it across the floor fighting against friction versus if you're going to put it on a dolly where you have a small lever arm. So you try and balance that thing so the center of mass of that washing machine is very close. A large force that is close to that axis of rotation versus this orange arrow, so distance to force. Small force at a long distance equals large force at a small distance. So how you tip this around and what it's pivoting around, it all kind of comes back to that neat little PhET simulation. So play around with the PhET simulation. If you don't get through the entire quiz, that's just fine. Get through as much of it as you can. And for this week, just really pay attention to your project. So this is hopefully the time to put kind of some final touches on that build, fix any problem areas that came up through the testing phase. If you would like to work on campus, I am there Monday through Friday, 8 a.m. to 2:30. Come on by. I'll let you into the makerspace or into the computer lab. We can talk through stuff together. Text me, give me a call, let me know what resources you can use, and play around with maybe some simple machines to add to your project. So adding a gearbox to it or a lever arm, add a wheel and axle somewhere to kind of help move stuff around easier. So just try and think of something that you can do to improve that design a little bit for this week. Okay, let me know how I can help you out. Hope you guys are doing good out there.